Let's play with volumes of solids with known cross-sections some more. Number 2A. We're going to use the same triangle shape from the first problem in the last video, but now we're going to do semicircles perpendicular to the x-axis. So if I try to visualize this perpendicular to the x-axis, here's going to be my semicircle. So I can start to kind of visualize what this is going to look like. But to do even better, here we go. Here's our triangle shape. I have it set to semicircle sections. If we tilt it, you can start to see what this 3D shape looks like. So there's my triangle. There's my semicircle cross sections. We can start to visualize what this looks like. So let's go back to our problem. This says to just set up the integral, don't actually solve it. So we know this should be the integral. This is in terms of x, and we want to do the area of our cross section, dx. Well, the area of our cross section, these are semicircles, so 1/2 pi r squared. And we know, now let's actually write this over here, that our limits go from x equals 0 to x equals 1. So now I just need to figure out what is r. Well, here, let's do this different colors so we can see this a little better. That right there is the base of my semicircle. But that's not r, that's d. That's a diameter across the entire circle. So if I want to actually find r, it's going to be half of d. So my radius is half of this whole diameter. Well, this diameter is the top curve minus the bottom curve. So there's my diameter, which means my radius is going to be half of that. So there's my radius. And now I can take this radius and put it into my area equation. So 1/2 pi negative x plus 1 squared. And that is the integral. And it says set up, don't actually solve. There's my limits, there's my area of my cross section. Let's try 2b. Now we want to do rectangles. So let me erase all this that I've got here. We want to do some rectangles, and we want these rectangles to be perpendicular to the y-axis, so like this. And we want all the rectangles to have a height of 1/4. So that means no matter how big the base is, the height of these rectangles is still 1/4. So to visualize this, here's our triangle shape. I have this set to rectangles. You'll see that my rectangles go perpendicular to the y-axis. Start to tilt this so we can visualize. All those rectangles have a height of 1/4. So there's my 3D object we can start to visualize. So let's do the integral. This integral is perpendicular to the y-axis, so my limits should be in terms of y now. In addition, and we want to do the integral of the area of my cross section. Well, this cross section is a rectangle. Rectangle is length times width. So our length, or our height, I guess I could say, is 1/4. And that's never going to change. The height of all of these is always going to be 1/4. So times by, now we just need to know what this width is. But since this is side to side, instead of thinking top minus bottom, we now need to think right minus left. And we need this in terms of y, not x. So if we solve this for x, we would get y minus 2 divided by negative 2. So if we want to do right minus left, we have our y minus 2 divided by negative 2 minus our left is just the y-axis, or 0. So that is going to be the length of these rectangles. And the area of these rectangles is that length times the height of 1/4. So I need dy, and I need some limits. These limits are in terms of y, so I'm going from y equals 0 up to y equals 2. And that would be the volume of that 3D shape. Okay, in the next video, we're going to talk about another volume, a new solid, but this one isn't going to be this triangle anymore. This one's going to start to deal with some curves, and we're going to see what that does to our shape.